Okay, let's just finish up this chapter 5.1, chapter 5, section 1, the mean and standard deviation for a discrete random variable. So we covered a bunch of this already, and we just finished showing that we just finished using this formula for the mean, mu, is equal to x p of x, and add all those up. And here, without too much discussion of it, we talked about the formula for the sigma squared as this. So you can see p of x and p of x are the same for this formula and for this formula. Sigma, of course, is the same. So the difference between these two formulas is here we have x, and here, if you remember what this was called, or what we might have called this, it was called the deviation of x from the mean. The deviation of x from mu. Remember, actually, we often write x sub I, but they're not writing the sub I here. But anyway, so what's the difference in this formula for this one, for mu, and for this one? So again, p of x is the same, sigma is the same. So the difference is here there's x, and here we can call this the deviation of x from the mean, and then squared. So you might want to remember it that way. Anyway, you can follow through here, and we said that when you do the calculation, you get 1.79. Now remember, this is not for data. This is for a probability distribution, right? We don't really have any data here. We just have this p of x table here, and that's what we use. We don't have data to use to calculate this. We have this p of x table, and we calculate this using that p of x table, using this. So you can do that yourself. You can check it. And then, of course, the square root of it for sigma. And, okay, so here, if we look at this graph, so okay, so there's the graph. Now, what can we say about the meaning of sigma? So we already said that the mean was 1.9, which is about here. So that's kind of the meaning in terms of the picture about the mean, right? It's located here. Okay, but what does sigma mean? Remember, sigma is about 1.3. Where's sigma? 1.34. So what does that mean here? So here's how they give some meaning to that. So they say the graph of this probability distribution is here. This is the probability distribution graph. Since the distribution is approximately mound-shaped, so they mean it's like this, as opposed to maybe this distribution is not mound-shaped, or this distribution that goes up, down, over, and down. This is not mound-shaped. This we would say is mound-shaped. This is maybe mound-shaped. So that's what they mean by mound-shaped. So this one is really, they wouldn't call it mound-shaped. This is like a U, actually. So it's not mound-shaped. So they say that since the distribution is approximately mound-shaped, so when the distribution is approximately mound-shaped, here's how we can use that sigma. It turns out that approximately 95% of all the measurements, so what do they mean by the measurements? So the picture is here. So remember that what are the possible values for x? So they are 0, 1, 2. Oh, we didn't even read what this was, by the way. But they are 0, 1, 2, 3, 4, and 5. Let's read what this is. So here's a store called Big Box. It sells a particular laptop that has only 4 in stock. The manager wonders what today's demand for this particular laptop will be. So she's wondering how many people are going to come to the store and ask for this laptop. So she learns from the marketing department that the probability distribution for X, the daily demand for the laptop, so of course we don't know what the demand is going to be for the laptop, but if we look at the past, well, sometimes nobody came for that and asked about that laptop. Sometimes one person came. Sometimes 2 people came. sometimes 3, sometimes 4, sometimes 5. And what was the probability that nobody came? 10% of the time in the past, no one asked for that laptop on a given day. 40% of the time, one person did. 20% of the time, 2 people did. So that's the meaning of this 1, 2, 0, 1, 2, 3, 4, 5. So what they do is they say find the mean and variance. Well, we already did that, and the standard deviation. And then, is it likely that 5 or more customers will want to buy the laptop today? So let's look. We can answer that also. So what they're saying, is it likely that you're going to get 5 people or more asking for the laptop? Well, I think all these numbers add up to 100, so, or rather to 1. So anyway, the chance that 5 people will ask for the laptop is only 5%. So we would call that unlikely, probably. So the answer would be no, it's not likely that 5 or more customers will want to buy the laptop. Okay, so going back to, and you can read that here. So going back to what is the meaning of the sigma? So here, this is what they're saying here is not always true, and it's not exactly true, but they're just saying in general, this is a kind of a statement we can make. So when we have something which is approximately mound-shaped, it will turn out that if you start at mu, what was mu? 1.9, so you start here, and if you go 2 sigma plus 2 sigma and minus 2 sigma, so sigma was 1.34, so 2 times that. So if you add 1.9, if you take 1.9 and add 2 sigmas to it, so what does that do? Start at 1.9 and go up 1 sigma, say, and another sigma, brings you up to something like here. And if you do going down from 1.9, it takes you 1 sigma and then another sigma down to here. So the actual numbers are, this is the calculation, these are the actual numbers. You go down to negative, actually I was wrong, you go down here, negative 7.8, and you go up to 4.58, we're way up here, so I was kind of wrong. Way up here, so if you go, so starting at 1.9, going up sigma, 2 sigma, sorry, and down 2 sigma, brings you from here to here. So what they're saying is if you do that, if you go between plus and minus 2 sigma, plus and minus 2 sigma, about 95% of all the data will be there. Now that sounds kind of impossible to say that for all possible probability distributions that are mound-shaped, but it is sort of true. Sort of true. So we do use this kind of rule. So now what about, in reality, what about ours? So down to negative 7.8, that goes down here. So that's everything below 1.9, that's covers everything if we go to negative. And up to 4.58, that's probably almost everything. So it does sound reasonable that we could say about 95% of the time will be in this range. Remember, what does this mean? The number of people that will come to the store to ask for it. So we're saying that basically the number of people will be in this range. So of course, you can't get a negative number of people, but anyway, this is the range that we calculated. So of course, that's pretty much true, right? Because 4.58 is almost up to 5, and we already said that just 5 is very unlikely, only 5%. So, so it is true in our case. And they explain that here, so you can read that here. Okay, let's do this example and this example. Okay, so example 5.3 is about a lottery, and it's going to benefit a local charity. And 8,000 tickets are to be sold, and each one is going to be sold at $10. So when they sell them, they will have collected $80,000. The prize is a $24,000 compact car. So you can buy a ticket for $10. If you win, you get this car. If you purchase 2 tickets, what is your expected gain? So we haven't really used that phrase, but we did use expected value. So what we have to do is define a random variable here, and then we'll ask what is the expected value of that random variable. And that's what they mean by the expected gain. So we want to define a random variable that represents the so-called gain. So they're going to do that down here. So here's the random variable. Now, why does it look like this? And why does it have probabilities like that? Let's read what they say. They say your gain, we're going to call it x, is going to take on one of 2 possible values. So one of them is this, one of them is this. And why are these the numbers? They say you will either lose $20. So in other words, there's only 2 things that can happen after you buy these 2 tickets. One is that you don't win the car, and the other is that you do win the car. So if you don't win the car, then you just paid $20, but you got nothing back, so you lost the $20. So one possibility is that you lost $20. And then we want to put the probability associated with that. And the other possibility is that you win, you get the car. Now you did pay $20, so you don't quite win $24,000. You win $24,000 minus the $20 that you paid. So this is your gain if you get the car. So it's not quite $24,000. It's this. So now we can see that there are 2 possibilities. So one is that you don't win the car, and that means you just spent $20. And the other is that you do win the car, which means you get the car, but you still spent the $20. So this is your net amount. Now, what are the probabilities for these? Well, we said that there are 8,000 tickets, and what are the chances that you win? Well, each ticket that you bought has a 1 in 8,000 chance of winning. Since you bought 2, the chances of winning are 2 out of 8,000. So the chances of getting this much money are 2 out of 8,000. And then the chances of losing the $20 is the rest, which is 8,000 minus 2 is this number out of 8,000. So this is the probability distribution for the gain. So now we can figure out the mean, which is what they asked us to do. What is your expected gain means? What is the expected value of this x, which we called the gain, or what is the mean? So we use the formula here, and your expected gain is minus, so when you do the calculation, you get minus $14. So how can we interpret what does this mean? They said, remember that the expected value of x is the average or theoretical population that would result if the lottery were repeated an infinitely large number of times. So in other words, if we played the game, we bought 2 tickets, and then we played the game again. The same structure, but a different lottery, but it had the same payouts. So when we bought 2 tickets, then we did it again and again and again. Eventually, or sometimes, we would actually win the car. But sometimes, actually most of the time, we wouldn't win the car. So we can think about, if we played many, many lotteries like this, what would be the net result? So sometimes you would win the car, but most of the time you would lose $20, and on average you would lose $14. That's what this minus 14 means. So they say, if this were done, your average or expected gain per lottery ticket would be a loss of $14. I think that's wrong. I think it's the expected gain per 2 lottery tickets. I'm not sure, but I think that's wrong. I think it should be per 2 lottery tickets. Your expected loss would be $14. Does this change your mind about playing the lottery? Okay, let's do one more. But to review, to figure out the expected gain, we have to define a variable x called the gain and figure out what are the possibilities for x and then what are the probabilities for those possibilities. So one of the possibilities for x is that it's minus 20, that is you lose, and you lose $20 because you paid for 2 tickets, and the other is that you win the car, and the net effect of that is this. And then you write the probabilities, and then we have the probability distribution, and then we can figure this mu out, which is the expected value of the game, we say, or the expected gain, or we could say the expected value of the game. But I think this is based on buying 2 tickets. What would it be if we only bought 1 ticket? This would be this over and 1 here, and this would be 7999. I don't know that we would get the same number here in that case. Okay, one more example here. An insurance company needs to know how much to charge for a $1,000 policy. And that policy insures in the event against cancellation due to inclement weather. So there's some kind of event, maybe it's a music concert, and the company that's sponsoring the concert wants to buy some insurance, and so they want, if they're going to sell a lot of tickets, and then they're going to have to pay back all those tickets if there's bad weather, so they're trying to get insurance on this. So they figure that they're going to have to pay back $100,000 to all the people who bought the tickets, so they want to buy a $100,000 insurance policy in case there's a cancellation of the event because of bad weather. So the insurance company is going to do some calculations, and they figure out that the probability of bad weather during the time the event is assessed is 2 in 100. So the chances that there's going to be really bad weather, so bad that the event will have to be canceled, is 2 in 100. So now they're trying to figure out how much they should charge for this insurance policy that they're going to sell to the music producers. And what they want is that their expected gain is to be 0. That's what they're setting up. Now, probably an insurance company won't do that. They'll probably want their expected gain to be positive, but in this problem, they're just trying to work out how much they should charge in order for their expected gain just to be 0. They're probably going to charge more than that so that their expected gain is more than 0. So the first thing we need to do is define the random variable, and we're going to call that X, and it's going to be the insurance company's gain. And C is the premium, or how much they're going to charge to sell this insurance policy. So we don't know how much they're going to charge. They don't know how much they're going to charge, but there's going to be 2 possibilities. There's a very small, there's only a, okay, let's go to here. There's only a small chance that they're going to actually have to pay out, but they might have to pay out $100,000, but they're still going to receive some amount, we call that C, from the people who are buying the insurance company, from the music producers. So they're going to have to pay out $100,000, but they received C, so the actual loss to them is $100,000 minus the C, so it's lost, so we put a negative in front. Now the chance that this happens, that this is only when the weather becomes really bad, and the chance of that is 2 out of 100, we said. On the other hand, they can, if there's not bad weather, they don't have to pay this 100,000 out, so they just get the C. And there's a 98 over 100 chance of that happening, 0.98% or 98%. So they want their expected value to be 0. Now, like I said, they probably want it to be more than 0, but suppose they just want it to be 0. They don't want to lose money, in other words. Then we want this formula, we want the expected value to be 0. So what do we get over here? We get C times this plus this times that. So C times this times that. And we want that to be 0. So now we can solve for C and figure out how much they should charge in order to, in the long run, not have to pay out, or their expected gain will be 0, not a loss. So if you solve this, I guess it ends up that C is 2,000. So if the insurance company charged a premium of 2,000, then the average gain for a large number of similar policies would equal 0. The actual premium would equal 2,000 plus administrative costs and profit. So they'd charge more than this, actually. They'd want to think about what their administrative costs are and what profit they want to have. So they would charge more by that amount. So you can look up this concept of expected value on the internet, and you'll probably find some nice videos on it. Now, this section has all been just for discrete random variables. We talked about the difference between discrete and continuous random variables. So we've been working with discrete random variables so far, and I think for the rest of this chapter, in fact. But they just mention here that when we do end up talking about continuous random variables, which should be chapter 6, then some of this will still be this, look similar. So the mean and the standard deviation for continuous random variables we'll still use the same kind of symbol here, and this will still be true. Sigma squared will still be the expected value of this. Now, we didn't go into this part here, but it will still be similar. But we'll have to, in this case, in the case of continuous, instead of using sigma, which we saw, we use sigma for both of the formulas, right? We use sigma here. For sigma squared, we use this capital sigma. And for this mu, we use this capital sigma. So we use sigma both times. But when you have a continuous random variable, you have to use calculus. And if you've studied calculus, you need the integral instead of sigma. So a symbol like this, instead of sigma, we would use this. Now, we're not going to use this. We're not going to have to deal with this. But that's what you would do if you had a continuous random variable. But the concepts are just the same. And here they say examples of discrete random variables, not continuous, can be found in a variety of everyday situations and across most academic disciplines. However, there are 3 discrete probability distributions that serve as models for many of these applications. We'll study those in the next few sections. So actually, we'll probably only have a chance to study one of them, which is in section 5.2, and we'll do that next.